give us an intuitive feel. The closest star to the sun is 4.2 light years away. Right? But if I started giving that to you in meters, it really wouldn't make any sense. All right, back to the Milky Way for a second. These are pictures of different sections of the Milky Way. And this is one of the things that's cool in astronomy. When you don't see something like this, what that really usually means is there's a cloud in the way. Right? There's an interstellar cloud in the way that's dark, and it's absorbing the light that's coming from the other side. Now, everything in the Milky Way, relatively speaking, is close to us compared to other galaxies, but so we see things like this. This is a cloud, this reddish area. This is a cloud out in the Milky Way that has a lot of hydrogen in it, and all the stars in this cloud are causing it to get excited. Right? And when it gets excited, it emits red light. Right? So we get this reddish cloud due to a lot of hydrogen. So you might know what hydrogen is? It's a gas. Hydrogen is our simplest element. Right? Hydrogen consists of one proton and one electron. That's the simplest element we can make. All right, now we step back a little bit, and we're well into things that we've had to construct based on astronomical observations, right? Here we are, we're the Milky Way. Near us, there are what are called the Magellanic Clouds. Magellanic Clouds are two small galaxies that I believe actually orbit our galaxy. Right? So just like we have planets going around the sun, we have a couple of small galaxies going around our galaxy. And then there are these dwarf galaxies out here. And by dwarf galaxy, it's just like dwarf planet. It's a small collection of stars, right, that are all together and held together gravitationally. Then over here is M31, the Andromeda galaxy. I'm hoping this semester to get all the equipment that we need in order to look at Andromeda. The reason I want to look at Andromeda, so the moon in the sky is about half a degree wide, right? So if you hold your hands out and you just hold up a finger, you get about half a degree, so about half a degree wide. It always looks bigger than that because of the way our eyes work, but it's about half a degree wide. Andromeda is actually about that big in the sky. It's about 6 times bigger than the moon. The reason we don't see it is it's so faint, we can't. All right? So what I hope to get this semester is a camera I can hook up to our telescope that can actually see it. And so we can look at it and go, wow, there's Andromeda. It's a big galaxy. It's relatively close as things go. It's, 3 million light years away or so. And then there's M33. This collection of galaxies is what we call our local group. And we're part of a bigger collection of galaxies that are about 50 million light years in size that's called the Virgo supercluster. Okay. So the Virgo supercluster is a bunch of galaxies that are gravitationally influencing each other over long distances, 50 million light years. One of the big mysteries big things we have yet to successfully measure, we know how fast light goes. We know how fast every other particle in the universe goes or can go. We do not know how fast gravity propagates. Okay? So, and it's hard to run the experiment. To run the experiment, you need to be able to do something like take the sun and shake it up and down and see how long it took for that to be noticed gravitationally out of the Earth, right? Well, it's really hard to shake the sun up and down, right? You know, it's hard to run the experiment. And so we keep looking for other clever ways to try and figure out exactly how fast does a gravitational wave propagate. We believe it propagates at the speed of light, but we don't have experimental confirmation, which is the kind of thing that bothers physicists and astronomers, right? We like to confirm things experimentally. Well, you know, when we get in the business of shaking suns, we'll let you know and come back with that. Until then, we're going to have to look out in space, which is what we're doing now, for something that happened and look for how long it took that gravitational effect to propagate through. All right? And that's what we do. We have to do a survey of the sky. The sky is deep. Right? Do a survey of the sky and look for an event that tells us, based on what happens after the event, how long it took for the gravitational effect to be felt. There are people working on this now.
Are there other galaxies that represent solar systems similar to ours?
So, even within our own Milky Way, we're beginning to find solar systems similar to us. The issue is, it took us a long time to find Neptune and Uranus and Pluto. Finding a planet that's around another star is hard. We've just now recently launched a probe that's in orbit around the Earth that's doing just that. It's looking for planets around other stars. We don't get to see them directly. We've only seen a handful of planets directly. So it's not like, you know, we do with our own solar system, where you get a telescope and you look at the planet. You get a telescope and you look at other stars, and then you watch for that star to do something that indicates there's a planet around it. So a lot of the early planets we found were big, Jupiter size and larger, right? The reason it's easy to find a big planet is because Jupiter actually makes our sun wobble a little bit. And so you can look at another star and you can see it wobble because of a big planet going around it, right? Just like the Earth-Moon system makes the Earth wobble a little bit, a big planet makes a star wobble a little bit. And so we found a lot of big planets early on because we look out at stars and we'd see them wobble. We also found a lot of big planets early on because what happens when, you know, if you pass your hand in front of the light over you? There's a shadow. And so we'd see a planet go in front of a star. We wouldn't see the shadow per se, but we'd see the star get dimmer and then get brighter. All right? And so we found, early on, we found big planets that way. The Chandra Observatory is looking for smaller planets, and that's the one that recently found, NASA announced recently, they found a planet that's in the habitable zone for its star. So Earth, our sun has a habitable zone. By habitable zone, we mean a region in which you could have water, right? Too close to the sun, you can't have water, it all evaporates. Too far away, you can't have water, it's all frozen. So there's a region, for us, we have 3 planets in our habitable zone. We have Venus, Earth, and Mars. So we have found one planet in the habitable zone of another star that is 1.6 times the size of Earth. So it's about the right size, it's in the right area. So when we talk about, are we looking for solar systems similar to ours, we now have the first candidate for, yeah, this is very similar to ours in that there's a planet in the habitable zone that's the right size. Okay. We found a lot of instances of planets, big planets, close to their stars, and they go around them really fast, because the closer you are to a star, the faster around it you have to go to stay in orbit. Otherwise, you go into it. We found a few with biggish, not big, you don't get Jupiter big, it'd be rocky, but you get several times the size of the Earth and it's still rocky, but outside the habitable zone, either too close or too far away. And we calculate where is the habitable zone based on how bright the star is, then we know how much energy the planet is getting from that star, and we know whether or not it's reasonable to expect water, right? So we know Right now, we're up to almost 2,000 planets that we found in the Milky Way outside our solar system. And we've only searched a small volume because that's all we can do. We can't see most of the Milky Way in a way that lets us see whether or not there are planets. So it's reasonable to assume that there are millions or billions of planets in the Milky Way, and that the same is true of Andromeda, and the same is true of M33, and the same is true of every galaxy in the Virgo cluster. Right? Lots and lots of planets. It's a normal process in forming a sun, a star. Part of the process of forming a star results in planets. All right. So, talked a little bit about hydrogen, which is our simplest atom, and we talked a little bit about gravity. Gravity wins in the end, but there are other forces out there, and there are other things we'll talk about throughout the semester that have to do with atoms. Right? Atoms are what make up everyday matter. Atoms, the term atom means indivisible. It's not true. Because atoms are made up of neutrons and protons and electrons. This is sort of an old orbital picture. It's not really like that. So you have your protons and your neutrons, which are really, really small. Right? Even when you take an atom, if this were an atom, the protons and neutrons would be a little pinhead in the middle. And most of the volume of the atom is the cloud of electrons going around it. And you should not think, again, the universe gets weird when we talk about the very small or the very fast. Right? So you can't think of electrons as going in orbits like this. Right? Otherwise, hydrogen would be flat. Right? You got an orbit, it'd be like a solar system, it'd be pretty flat. One electron going around one proton. That's not the case. The best thing we can say about electrons, and when we do the quantum mechanics for where electrons are in orbit around a nucleus, we come up with these weird shapes. And what that real shape says is this is where you're most likely going to find the electron. It's not really, when you get into the really small, you talk about where you're most likely going to find something, not where something is. The quantum mechanical statement about us is we're most likely here. We're not necessarily here. Right? We're just most likely here. Now, when you get into large macroscopic objects like us, the odds that we're here are 0.99.99999999999% that we're right here. You know, the odds that we're spontaneously somewhere else are very little. Never happens. That's not true for little bitty objects like electrons. They can show up in different spots. So the forces governing the atom. Your book talks about the weak force, because I'm a particle physics person, I changed that to electroweak. The electroweak force, the strong nuclear force, and gravity. Those are the forces that operate on all matter, right? Gravity wins in the end for several reasons. The strong nuclear force has a very short range. The reason that uranium decays is because its nucleus is big enough that the strong nuclear force no longer acts on bits of the nucleus that are too far away from each other. So they're not held together as tightly as a smaller nucleus. And so uranium decays. Just does it spontaneously, right? The weak, or the electroweak force, is how light gets created. It's how we push around electrons all the time. It describes the interaction between protons and electrons and neutrons and electrons. So electroweak force is another force that we use all the time, but it's also short range. And also depends on the fact that overall the universe is neutral in terms of charge. So electric charge doesn't have any long range effect simply because most matter is neutral. All right, so atoms we'll talk about more when we get into observations, astronomical observations, because atoms, I'm trying to think if there's a good analogy out there. You can excite an atom, okay? But because of quantum mechanics, you can't excite it to any energy. It has distinct energies it goes to, right? And so, while we look at out in astronomy, we look for atoms that got excited, and then when they go back to the lower energy state, they emit a photon that's always exactly the same color. And we use that in making observations to determine what is stuff made out of. One of the big mysteries for the longest time, hydrogen is the most abundant element in the universe. And in fact, you have a bunch of it right there in your bottle, right? Because hydrogen is part of water. But early on, people thought hydrogen was rare. So the only place they saw the spectra for it was in the sun. And then they happened to see the spectra for it in a volcano. You know, oh wow, so maybe hydrogen is only in places where things are hot. Right? But no, hydrogen is actually everywhere. It just usually gets bound up in something, like water. We're using it all the time. It's rare that it's by itself, but it's the most abundant element in the universe. All right. The last bit, dark matter. It's called dark matter because we cannot see it. All right? It makes up about 80% of the universe. We do not know what it is. We cannot see it. We cannot interact with it. It's the big astronomical mystery of the day. Along with dark energy, which seems to be making the universe expand. So these are our big mysteries for today. Things we still do not understand. Dark matter, dark energy. These are some of the big, along with the search for extrasolar planets, these are some of the big questions today. All right? What is this stuff? Since it seems to clearly be important. All right. Last bit. And then you can all wake up and go. Right? The last bit. I need to remember to get you guys to exercise in the middle of class. I'm walking around, I'm awake, but you guys are like, I think it gets a little warm during the class. You know. All right. A big miscommunication between the scientific community and the general populace usually revolves around the word theory. Because usually we mean something different by the word theory than people that use it in the general populace. All right? Scientists mean something very specific by theory. We begin with what's called a hypothesis. Our hypothesis is our guess. Our hypothesis is our, hey, there's a little bit of data, I think it means this. Right? By the time we go from calling it a hypothesis to calling it a theory, we've done a lot of work. And we've done a lot of measurement and a lot of investigation, and we're getting closer to, yeah, we actually are really solid on, we believe this is what's happening, right? We still call it a theory. Why? Because we can't run every single possible experiment that exists, right? We might be so solid, like we do not believe this is ever going to stop being what we believe, but we're still going to call it a theory. We have Newton's laws of motion, which were called laws for about 200, 300 years because we didn't have any counter to it. But then came special relativity and quantum mechanics, and we suddenly knew, oh, all right, that doesn't quite apply everywhere, right? So, but the places where it doesn't apply are way out at the edges. Right? For the vast majority of everything, Newton's laws of motion still apply just fine, unless you're itty-bitty or moving really fast. Okay? So it's at the extremes, and this is why modern physics, we tend to always call something theory, because we believe at the extremes we may still find something that disagrees with our model that we've come up with. But by the time we call it a theory, we've got a model and we've tested again and again and again and again and again. Right? And we keep testing. Let's see, is that it? Am I done? Are we done for the day? No, there's one more. Oh. All right. This isn't really. Okay. So this is just a step through, right? If you imagine the whole universe, the Virgo supercluster is an itty bitty speck. Within the Virgo supercluster, we're a little speck, right? Our local group is a speck. Within the local group, our galaxy is a speck. Within our galaxy, our sun is a speck. Within our sun, the Earth is a speck. Right? So, the Earth is, one of your problems in this first part is take the quad, 250 meters long, according to Google Maps, right? And tell me how big the solar system and planets would be if you made the quad the solar system. So if we start with the sun at the Union, right? How big would Neptune be way out at the street? And where would the other planets be? Right? If you put the sun at the Union, what you're going to find when you go through and do this, most of the planets don't get you off the sidewalk. Well, the inner planets don't get you off the sidewalk, right? And then you have Jupiter, Saturn, Uranus, and Neptune. All right. Any questions? Thoughts? Confusions? Ideas? Yes?
Is it what you just said?
It's on Canvas.
Okay.
It's all on Canvas. Yeah. One of the things you'll have to watch for, I will not mention assignments that are due because it's all on Canvas. That's why you need a Canvas app and you need to have it so you are check Canvas on your computer since you've got it in front of you all the time. Yeah, this is what's going on. Most of it's easy, right? Most of it's easy. All right, I'll see you guys Tuesday.